Monday's class didn't record, but it's fixed. So you won't see anything on YouTube for lecture 26. Okay, so the reason it's important that you, why is this beeping at me? I don't know. Okay, so the reason is because next Wednesday's quiz will be on class 24, which is quadratic functions. That homework's due tonight. And then classes 26 and 27, which were Monday's class and today's class. So remember, this is just one section in your book. This is just section 3.2. So basically, you have 2 sections on the next quiz. Quadratic functions and 3.2. Why are you beeping at me? Are you going to make a liar out of me? And not record? Well, we'll find out if this records. If it doesn't, I did record my first class. Okay, if you have any time over the next couple of weeks, I have lots of sign-up time on my door because it's advising week, but you're welcome to put your name in any half-hour slot. If you want to come for extra help on anything, I'd welcome you. So even if, I don't know why this is beeping. It's like beeping. I have like a voice in my ear almost. Sorry. Okay, I'll try to record this if I can. All right, so let's go to number 12. We finished 11 on Monday. So 12 is the last idea we have to talk about so we can start today's lecture. So 12 says we have reached a turning point, okay? And we know our polynomial functions have turning points on them. They're either relative maximums or minimums. Sometimes they can be, depending on the graph, they could be absolute minimums or absolute maximums. But in this case, looking at this picture, we have a relative max here at -1.6 and a relative minimum at 1.5, -0.875. And let's fill in the rest of this function, which didn't come through on mine. What does it say there? X cubed minus x squared minus what? 4x plus 4. Okay. So when it's in polynomial form, how do we determine the degree of the function? What do we do to find the degree of the function when it's written as an addition and subtraction expression? When it's in terms, what's the degree of this particular polynomial? The highest exponent. So the degree here is 3. Okay. It says to recharge my headset. Uh-oh. So I think I might be able to do this. Hang on. Let me just finish this and then I'll go get my little charger. How many zeros does F have if you look at the graph? How many zeros are there? 3. And they occur at -2, 1, and 2. So we have 3 real zeros. Okay. How many turning points does this graph have? 2, right. It turns around here and it turns around there. So we have 2 turning points. So what happens at each turning point? How would you describe what happens to your function? And the way you think about that is say, okay, what's my function doing to the left of -1? And what's my function doing to the right of -1 before it hits that turning point? What's your function doing from -infinity to -1 on that interval? Here's your interval. What's your function doing on that interval? How do we describe what's happening to the function over that whole interval? Remember, you're starting way down here. It's increasing, right? So over that interval, your function's in. So let's pick the turning point -1.6. So from -infinity to -1, your function is increasing. And then from -1 to 1.5, remember these are over your x values, from -1 to x equals 1.5, what's your function doing? Decreases, right? So it's increasing on this interval and then it decreases over that interval. So the turning point says you're going from being an increasing, in this particular case, from being an increasing function to then being decreasing. Okay. Let's look at our next turning point. So let's look at the turning point -1.5 negative 0.875. We've already determined that from negative 1 to 1.5 over that interval, my function is decreasing. And then what's happening, from 1.5 to positive infinity, what's happening to my function? From x equals 1.5, which is right here, all the way out, what's my function doing? Increasing, right? So you see here, your function turns around from being a decreasing function to an increasing function. So what I told my other classes, this is like a lot of our lives, okay? We have mood swings, right? We're kind of moving along, being positive, increasing, and then we hit some point and we start to feel down, and something good happens, we start to go back, swing back up. Okay, so it's the highs and the lows of our natural rhythm, and that's what polynomials are. So notice that if you know the degree of your polynomial, there's something you can determine. If you know your degree, you can always determine the maximum number of turning points. So if you had a cubic, you can say that at most you're going to have 3 take away 1, which is 2 turning points. That's the most number of turning points you can have for a cubic. Doesn't mean you'll definitely have 2 turning points, and I'll show you in a minute an example. Okay, and it also tells you the most number of real zeros you can have. The most number of real zeros you can have with a cubic is exactly equal to the degree. So you can have at most 3 real zeros, and at most 2 turning points. That's a very important property that we're going to use for graphing polynomials. So let's take a look at an example where you wouldn't have, say, 2 turning points or 3 real zeros, but you're a cubic. Can anybody give me a cubic function where you wouldn't have 2 turning points in it, or you wouldn't cross your x-axis 3 times? Do you know a cubic function that would look like that? 1 over x cubed, that's not a polynomial function, that's a rational. So flip that around and what would you get, Adam? X cubed, right? That was one of our parent functions, right? That's a parent function that's a cubic. It's always increasing. It flattens out at 0, 0. It starts to flatten out. It doesn't become a horizontal line. So here's a cubic that's always increasing. On the interval negative infinity to infinity, it's increasing. So it has no turning point. So we went from a cubic that had 2 turning points to a cubic with no turning points. And it doesn't have 3 zeros. It has 1 0, 1 real zero. Okay. Notice this word in front of the 0, real number, is important here. You'll see why later on. Okay, so this thing's telling me I need to charge it. So I'm going to stop the, so that's where we finished off with class 26. So let me just take a minute to stop this recording. I'll go see if I can charge this up somehow. And why don't you all right, so let's take a look at today's lecture. So now that we know about end behavior and zeros and turning points and multiplicities, we're going to be able to start getting some quick sketches of polynomial functions. So let's take a look at this first function. When you look at that polynomial, it's in polynomial form. What degree is it? What degree is it? 4, right? So that tells you it's an even function, even degree function, even degree function. And so you know that even degree functions have the same end behavior. And to determine what that end behavior is, you look at the leading coefficient. The leading coefficient is right here, it's 1. So a sub 4 is 1, and 1 is positive. So you know before you even start this graph that your arms are going to be up in the air. That's your end behavior. As x moves towards plus and minus infinity, your graph is going to rise on both ends without any bound. All right. So let's see. To find our x-intercepts, we set our y value, or f of x value, equal to 0, and then we factor this thing. So how are we going to start factoring this? What are we going to do here to factor the right-hand side of that equation? You factor out x squared, your greatest common factor, right? Greatest common factor is the first step of factoring. So we have 0 equals x squared. We have x squared minus 6x plus 9 left. And then we ask if it's completely factored. And we know x squared can't be factored anymore. So the question is, can the second degree trinomial, x squared minus 6x plus 9, be factored any further? Yes. In fact, it's a perfect square. It's x minus 3 times x minus 3. So this is x minus 3 times x minus 3. Those are the factors of 9 that add up to 6, 3 and 3. And now we want to take our factorization and make it more compact, which means if we have repeated factors, we want to use exponents so that we can deal with our multiplicities. That helps us with our graphing. So this is x minus 3 squared. So that's how I make it more compact, by using my exponents. Now I set each of my original factors equal to 0. My first factor is x. I set that equal to 0. I'm done. There's one of my zeros. And I set one of my other factors equal to 0, and x is 3. So I know on my graph that I will have x-intercepts because my zeros of my function appear on my graph as x-intercepts. So I know on my graph I can plot these 2 points. So I'm going to go down to my graph right now, and I'm going to put a dot in at 0, 0, and a little dot in at 3, 0. The other thing I'm going to do is I'm going to put sort of my end behavior on the graph up here. I'm just going to put the 2 arrows going like that, because I know I have the same end behavior as I move to positive and negative infinity. So with that little bit of knowledge, I can already get that far. Now I'd like to know, what is my y-intercept? My y-intercept is when x is 0, I want to find f of 0. So I throw 0 into that function. Everything's being raised to a power. 0 being raised to a power is always going to be 0. So 0, 0 is not only my x-intercept, but it's my y-intercept as well. So here's where we're going to need a little bit more of a review, because it's been a while since we've talked about even symmetry and symmetry about the origin. So let's review this real quick. I'm just going to pull off a little separate sheet here. You maybe want to put a little additional paper beside your notes, or find some space in your notes. Remember, even symmetry is defined. So let's take a look at 2 graphs that helps us to understand even and odd symmetry. Okay. Even symmetry, the one function you probably always want to keep in mind with even symmetry is just your graph. That has symmetry about the y-axis. And to prove that a function has y-axis symmetry or even symmetry, you have to show that f of x is equal to f of negative x. So to help you remember that, just think of two specific points on the graph that shows this symmetry. You know, if you put 2 into x squared, you get 4. And if you put its opposite in, you also get 4. So that's what this says. Look, if I take a value for x, I plug it into my function, my outcome, my output, my y value, however you want to think of it, is the same exact point above the x-axis or below the x-axis as when I put in its opposite value. And you can see that right here. 2 and negative 2 are opposite values of x, but their y values are exactly the same. So you have to show this not for one point on your graph, but for all points. So you have to do this for f of x and f of negative x. So you know what f of x is. F of x is x squared. Now what would f of negative x be? That looks like negative x squared. Now the question is, are those two sides the same? Well, to help you out, put -1 in front of that x instead of just the dash. Now use your rule where it says, if you have multiplication inside your parentheses, then your power attaches itself to each half. So you have x squared, you have -1 squared times x squared. That's x squared. That proves you have symmetry about the y-axis. For all x's and opposites, not just for the particular one you pick. Origin symmetry, remember, is our cubic. So what happens when we pick a value like 2 with the function, let's call this x cubed. What happens when I pick its opposite value, -2? What happens? Where do I go? So I come back to 8, -8. So now I can't say that f of x equals f of its opposite. The y values are not equal. How would you describe the y values? If you put in opposite x values, what happens to the y values? How would you describe a relationship between 8 and negative? They're opposites. So you say, if I put the opposite into my function, the opposite x value, I don't get equal y values, I get opposites. So the way we write that is we say equals negative. So let's see how this would work with our cubic function. So our cubic function f of x is called x cubed. When I put a dash out in front, it looks like that. -1 times x cubed. Now let me evaluate my cubic function. I input the opposite of this. You know that when you cube each one of those factors, you get -1x cubed. That's how you prove something has symmetry about the origin, odd symmetry. So if we go back here to our graph, well, first of all, it's degree 4. There's no way it's going to have odd symmetry. Okay? So what you really need to do is check, does this have even symmetry, or does it not have any kind of symmetry at all about the y-axis or the origin? So what you want to do is you want to perform this test. If I take a value for x and plug it into f of x, this is what I get, x to the 4th minus 6x cubed plus 9x squared. That's f of x. I want to see if that's equal to f of the opposite of x. So everywhere I see x, I'm going to replace it with -x. And I have to use parentheses. Oops, minus. Put a minus here. Minus 6 times -x squared cubed plus 9 times -x squared. Okay, so on this side I have x to the 4th minus 6x cubed plus 9x squared. And what do I get on my right side? What happens when I raise -1x to the 4th power? What do I get? X to the 4th, because -1 to the 4th is 1, and x to the 4th is x to the 4th. So it's kind of looking like maybe I'm okay here. Right? My x to the 4th matches my x to the 4th. Now I come to -1x cubed. -1 cubed is what? And -1 times a -6 gives me a plus 6x cubed. And that's where I don't get my match. Nope. Doesn't even matter whether the n comes out to be 9x squared, which it does. It doesn't match the middle term with your cube, because if you put in an opposite value, you're going to get opposite results. So this doesn't have either type of symmetry, neither one. So, okay, you say, all right, so this is not going to flip over the y-axis and have a mirror image, and we're not going to be able to rotate this around the origin either. So what can I do? Well, you use this very last step. Let's see what's the maximum number of turning points I can have. Well, my degree is 4, so the maximum number of turning points is 3. Maximum number of turning points. I may have 3, I may have less. My maximum number of zeros is I could have at most 4 real zeros. And you look at your picture and you say, well, in this particular case, I don't have 4 real zeros, I only have 2. So I didn't reach my maximum. I didn't cross my x-axis 4 times with real numbers, but I can cross it 2. So this is where we're just getting a quick sketch. What do you know about the multiplicities of each of these? What do you know about the multiplicities of each of these zeros? What's the multiplicity of this zero right here? Well, let's look at x. What's its exponent? Square, right? So it has multiplicity, Buddha, what? 2, multiplicity of 2, which means at 0, it's going to look like a little baby parabola. And what about 3? What's the multiplicity of the 0, 3 if you look at it? 2. Right. So both of these zeros have a multiplicity of 2. So when you go down to that 0 on your graph, just do something like this. You know you're going to end up with your arms up. So I would just put in a little teeny U shape, just like that, those zeros. So I know I'm not going to cross my x-axis. I'm just going to be turning around at them. So now you're all set to go. You say, okay, I start out way up here at positive infinity. I'm coming down to this 0. When I get to that 0, I turn around. I become an increasing function. Not for too long, because then I got to head straight back down to my next 0 and turn around and go up to positive infinity. I kind of took a little sharp turn there, so let me do a little better job. So you turn around there and you head up. So it kind of looks like a W.
How do you know that?
I don't. So that's my next point I was going to make. Right now, we don't know whether we turn around like right around here at 3, or whether we go a little bit higher, like up to 5, and then come back down. Or maybe we're even really low like this, right? We don't know how high up above the x-axis we go, between 0 and 3. But we do know it's going to be halfway between there. We're going to reach some type of maximum value. And in my first class, we actually looked at this, and the maximum value is like 506. It's just a little bit like this time. Okay, but for our purposes, we're not interested in, you just want to do something that's reasonable. We don't know how high above the x-axis. The only way you could figure it out a little bit is to take some numbers between 0 and 3, plug them into your function, and just see what is your highest value. All right, at 0 your function is 0, and at 3 your function is 0. So I think I still have it on my calculator here. Let me see. Open up. Where are you? All right, I'll close you. Hiding here somewhere. Yeah, I know. I just wanted to show you. I think it's still on. So, no, it's not. Is that it? Yeah. So there's our function. And so I'd be interested just looking at my table of values. My table, if I go from 0 to 3 and I increment, say, by a tenth. Let's look at my values, my y values. At 0, I'm 0. And as I start moving towards 3, I notice my y values are increasing, 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 and then I start to go down again. So right around 5 is where I reach my max. At 1.5, I reach my maximum value. So what I told my first class is, if you know a little bit of calculus, you can find that spot exactly. And that's what we calculated. It actually doesn't do calculus, it just does so if you wanted to find that point exactly, and you knew a little bit of calculus, then you look at something called the derivative in calculus. Okay, but I can't teach you a little calculus right now. So right now, our only concern is as long as you have some type of W-shaped graph here. You know your turning points. Okay? And you see you have 3 turning points here. One at x equals 0, one at x equals 3, and somewhere in between you have another turning point. Adam?
Once you factor out those zeros, that equation squared, and you know your transformation, say you got x squared, you should that one. X minus so you know your
Yeah, you can do test values on either side, but I'll just give you one more explanation. One of the things a derivative does in calculus is it tells you the slope of the line tangent to a point on a curve. So if I'm trying to find this value right here, I take the slope of the line tangent to that point. Well, guess what? The line tangent to any relative max or min, or max or min, is horizontal. So the slope of that line is 0. So you set your derivative equal to 0 and you solve. Now you don't know how to find a derivative. Can I do it pretty easily for you? No. So I'm not going to do it. It would involve too much. If I take the derivative of this and set it equal to 0, it'd be too much work. That's the x value that it occurs at, and then throw it into your function. Okay. All right, so try this one at your seats, okay? Try using those steps at your seats. And use your flags if you need any. Okay, so we know this is an odd degree polynomial. The leading coefficient is 1. So our right arm is up in the air, and our left arm is down in the air, heading down towards negative infinity. What were the 3 zeros you all found? What were the values? In order from smallest to largest. Negative 2, comma, 0, comma, 3. Okay. Negative 2, 0. F of y, excuse me, f of 0 is our y-intercept. That's also 0. So 0, 0 is both our x-intercept and our y-intercept. When we factor this, what does it look like? X times x minus 3, x plus 2, right? When we put it in factor form. Notice all of these have multiplicity of 1. So all of our zeros have multiplicity of 1, which tells us at each 0, we're crossing the x-axis. At each 0, we cross over the x-axis. Okay, we don't have to worry about symmetry about the y-axis. Okay, so we have symmetry about the origin. So to test that out, we check out this definition. If I take f of opposite values of x, my y values are opposite. That's what it says. Just think of your cubic function. So, well, the opposite of f of x means I change every one of these signs to its opposite. So I get negative x cubed plus x squared plus 6x. That's the right-hand side. Now to figure out f of negative x, I put into my function negative x. So I put negative x in for x and I cube it. I subtract negative x squared and I subtract 6 times negative x. And now I have to determine if the left-hand side of that equation equals the right-hand side. That's the question. Negative 1x cubed is negative x cubed. So far, the first 2 terms match. Negative 1x squared gives me a positive 1x squared, or x squared. So then I have minus x squared, and that's where I fail. This and this are not equal. So this has no symmetry about the origin and no symmetry about the y-axis. All right. So now I'm pretty much, it says, what's the maximum number of turning points? I have degree 3, so my maximum number of turning points is 2, the maximum number, and the maximum number of zeros, I can have at most 3. And you can see I have 3 there. So I'm going to head from way down here. I'm going to head for that first 0. I got to cross over. I know I'm going to cross back through here and cross back through there. So I got to go up and turn around, come back down, turn around again. I don't know how far up I go or how far down I come. That's not what's important right now. I'm just trying to get a quick sketch. So that would be a quick sketch of this particular polynomial. Any questions on this? Any questions at all? Okay, so the one we did together and the one you worked at your group, notice this is an important thing to remember. The 2 problems I gave you, your function is written in polynomial form. It's an addition and subtraction problem. You look for your highest power. When we switch over to number 4, is your polynomial now given in polynomial form? Do you see a big addition and subtraction expression on the right-hand side? No. What do you see? What kind of operation is between all of these? Multiplication. So this is called factored form. Okay? This is in factored form. So remember, your factored form is really helpful because you can look at it and get your zeros. Boom, boom, boom. You don't have to factor the darn thing, right? So the little tricky part comes in is remembering what degree you have. Because the degree is, if you were to multiply x plus 2 times x minus 2 using FOIL, you would get x squared minus 4. And then you'd multiply x squared minus 4 by negative x squared, you would wind up with x to the 4th power, negative x to the 4th power. You don't have to think about multiplying it all out to get the degree. You just look at each of your exponents and you add them up. So you add the exponents only when it's in factored form, not when it's in polynomial form. So the degree of this particular polynomial function is 2 plus 1 plus 1, which is 4. So it's an even degree. A sub 4, which is my leading coefficient, is right there. It's negative 1. So I know my leading coefficient, A sub 4, is negative. So that tells me both of my arms are going to be going down towards negative infinity as x approaches positive and negative infinity. So this function is going to fall. Drop, drop, drop. All right. Now all I have to do is to find my x-intercepts. It's already in factored form. Thank you very much. Set that equal to 0, and I say, okay, this will be 0 when my first factor x is 0. It will be 0 when my second factor is negative 2. And this will be 0 when my third factor is positive 2. What are my multiplicities at each 0? So here are my zeros. 0 equals x equals 0, x equals negative 2, and x equals positive 2. So I go back and check out the exponent on each 0. The exponent on this 0 is a 2. So that tells me it has multiplicity 2. Okay, spell it right, multiplicity 2. What's the exponent on x plus 2, the factor x plus 2, where negative 2 is your 0? It's 1, so it has multiplicity 1. And same with the factor that is x minus 2, which has 2 as a 0. It has multiplicity 1. So that means I go to my graph, and I know I'm going to go straight through there, and I'm going to turn around there. Now, how high above and how low you go, we don't know. Not without calculus or a bunch of test values. So you start way down here, you head up to your first 0, You're going to come up some distance, and you're going to come up. Am I doing this right?
I think the middle was upside down.
Yeah, right. So I did this a little too fast, right? All right. I know I'm coming straight through there, but I'm going to turn around here. Then I'm going to come up again, and then I'll go down. Now again, I don't know how high these hills are here. I don't know my relative maximum values. All I know is I go up some distance, some value of some unit above the x-axis, some height, and I come back down, turn around. This is a turning point. Notice we have 3 turning points, and that's 4 takeaway. 1 is 3. We have 3 zeros. We could have had a maximum of 4, right? Real zeros? But we only have 3. So a graph like that kind of makes sense, I hope. Any questions? What kind of symmetry does this graph have? Y-axis symmetry, right? You can fold it right over on top of itself. All right, so 5 is going to be, when you're bored this weekend and you want a little extra work, try 5 on your own. I want to get you right to the fun stuff. You have 2 activities. You have this activity, and notice the directions. I've even underlined. If possible, sketch a graph of a polynomial that satisfies these conditions. A is the leading coefficient. If it's not possible, you just say, no way, not possible, can't do, can't fool me, Kavanaugh, whatever you want to say. Okay? You've got 3 or 4 of those. Then you have match the polynomial to the graph. Okay? So you can start wherever you want. You can work by yourself, work with your group. Group can decide we're going to work together on a particular thing. Okay? So you have 20 minutes to I'll roam around and help you out. Put up your flags if you have questions. Okie doke?